Here's a trick. I write down a sentence. The enterprise operated across state lines. I hand it to a search engine that has never seen that sentence before, and it comes back instantly with the 5 most related passages out of thousands, session notes, predicate specs, an old debugging log. No keyword matched. Nothing was tagged. It looks like understanding. It feels like the machine read everything and knew. Here's the whole trick. Every passage was turned into a list of numbers, a point in space. My sentence became a point too. The engine measured which points sit closest, the angle between 2 arrows. That's cosine similarity. That's all of it. A magic trick that isn't magic, it's geometry. And the interesting question is not whether the trick is impressive. It is. The question is what geometry can do for you and what it can't. I'm Janet. This is the second video in our first topic, why theorem provers instead of semantic searches. Last time we priced hallucination. Today I want to be precise and fair about what semantic search actually does, because we use it every single day and we'd be slower without it. And then I want to show you the one line it cannot cross. An embedding model reads a chunk of text and produces a vector, hundreds or thousands of numbers. Train it well, and texts that are used in similar ways land near each other. The court dismissed the claim, and the judge threw the case out. Different words, neighboring points. That's the real achievement here. Nearness in this space tracks aboutness. Not spelling, not keywords. Topic, phrasing, role, whatever used similarly means in the training data, distance learns it. So retrieval becomes geometry. Embed the query, embed the library, return the nearest neighbors. Blend in a keyword channel for exact terms, fuse the 2 rankings, and you have modern semantic search. And scale is nearly free. 1 million chunks index once and answer in milliseconds. No schema to design, no ontology to maintain. The space organizes itself. This is why paraphrase search works when keyword search fails. Nobody wrote a rule connecting dismissed to throughout. The geometry carries it. For 20 years, we taught ourselves to guess the exact words a document used. Embeddings quietly retired that skill. Let me show you ours, because I don't want this to be a straw man. Our whole constellation runs on a vendored search engine called memsearch. Every working session writes plain markdown notes, decisions, dead ends, gotchas. Those files are the source of truth. An indexer chunks them, embeds each chunk with a local model, no API call, just a CPU, and stores the vectors in a small database. When a new session starts and an agent asks, "Have we seen this bug before?" the recall is a hybrid search. Dense cosine similarity on the vectors, a classic keyword pass alongside it, and a re-ranker fusing the 2 lists. And it is genuinely load-bearing. Each subproject keeps its own collection, so a legal session recalls legal memory, and a trading session recalls trading memory. Months of decisions stay reachable in seconds. If it vanished, we would feel it the same day. Notice the design humility too. The markdown stays the source of truth. The vector index is derived, disposable, rebuildable from the files at any time. Nobody trusts the geometry with custody of the record. It only gets custody of the finding. So when I tell you in about 90 seconds what this machinery cannot do, hold on to this exhibit. The critique is not embeddings are bad. Embeddings are one of the best recall tools ever built. The critique is about category. Now watch closely. This is where the trick stops. Take 2 sentences. The payment was made on time. The payment was not made on time. Embed both, with the very model our own memory runs on, and measure. The score comes back higher than the one for a genuine paraphrase pair. The engine finds these 2 sentences more similar than 2 sentences that actually mean the same thing. Same topic, same entities, same phrasing, 1 small word apart. To geometry, they are neighbors. To a court or a ledger, they are opposites. That is not a bug in the model. It's what similarity is. Distance in embedding space measures what a text is about, not whether it's true, and not what follows from it. Ask a nearest neighbor engine, what have I written that relates to this claim? It answers brilliantly. Ask it, does this claim follow from these premises? And all it can ever say is that the claim sits near things that sound like the premises. Looking like a valid conclusion and being one are different properties. Retrieval ranks, it never checks. And the higher the stakes, the crueler that gap gets. A retrieved passage that almost supports your argument is more dangerous than no passage at all, because it arrives wearing the confidence of a top-ranked hit. Here's the picture I most want you to keep. 2 graphs, 1 screen, drawn by the same rendering kit our own products use. On the left, an embedding cluster. Every dot is a chunk of memory, and the layout pulls related dots together. Now look at its edges. None of them asserts anything. Nearness is the only relationship in the picture. No direction, no order, no therefore. You can point anywhere and ask, what's around this? And that is the only question the picture can answer. On the right, a derivation tree. Same kit, different universe. At the leaves, predicates, small named claims. Above them, the axioms those claims become. At the root, one theorem. And every edge is directed and earned. It exists because a proof checker verified that exact step. Pull one leaf out, watch the right side. The root doesn't drift a little farther away. It stops existing. That's the category difference in a single frame. The cluster says, these things are near. The tree says, this follows from that. On the left, you navigate. On the right, you conclude. And no amount of better embedding turns the left picture into the right one. More data sharpens the neighborhoods. It never grows an arrow that means, therefore. The tree on the right is real, by the way. It's the shape of our civil RICO framework, the first golden framework in the proving kernel. The labels you see are synthetic, a demo fixture, Doe versus Acme, invented for exactly this purpose. But the structure is the shipping structure. Predicate leaves, axiom nodes, and a top-level theorem assembled by introduction rules, the lean kernel checks one at a time. The root is a disjunction. A civil RICO complaint is valid if any of 4 statutory routes holds, and each route is its own small tree, its own introduction theorem. Structure, all the way down. Nothing in it was retrieved. Every node was derived. And here is the honest sentence, said once, plainly. When that root lights up, the kernel certifies exactly one thing, that the conclusion follows from the stated predicates and axioms. It certifies nothing about whether those predicates are true of the world, or whether the encoding is faithful. We don't claim the conclusion is true. We make disagreement auditable. The tree shows you the exact predicate to challenge and lets you rerun it. That is still a different universe from a ranked list. A ranked list ends the conversation with, here's what's similar. A derivation ends it with, here's the step to attack. So, right tool, right question. Have I seen this before? Semantic search. It answers in milliseconds, it's cheap, and it's usually right. And when it's wrong, the cost is a moment of your attention on a bad hit. Does this follow? That's the kernel's question. It's slower, it's fussy, it wants every premise stated, but it's slow and rarely wrong, not never. The predicates feeding it can still be wrong, and when the stakes are a courtroom filing or a portfolio claim, that trade is the entire point. The failure mode this channel cares about is using Tool 1 on Question 2, retrieving something that sounds like support and treating it as support. That isn't a search engine defect, it's a category error by the user. And an LLM answering from its training distribution is, in this one respect, much closer to the left picture than to the right. Which is why both live in one repository, permanently, on speaking terms. In our constellation, the search side feeds working memory. Agents recall past decisions before they act, across every subproject. The kernel side gates the claims. Nothing verdict-shaped ships without a derivation behind it. Neither replaces the other. Neither is embarrassed by the other. And they even meet in the middle. What the search recalls often becomes the raw material a predicate is written from. Recall proposes, the derivation disposes. That handoff, geometry finding it, a kernel checking it, is the shape of everything else on this channel. Cluster for recall, tree for conclusions. The discipline is simply refusing to let the first one impersonate the second. Next time, the thing that checks the tree. The Lean 4 kernel, a proof checker small enough that one careful person can read all of it, and why that smallness is the entire trust story. The scripts and the kernels are at github.com/Quantapix. The longer map is at quantapix.com. See you in 1.3.